Okay, so this is the angle of elevation 1.2637, and then you drive 25 miles down the road, and there's an angle of elevation of 2.015 degrees here. Okay, and so you don't know how far you are from the base of the mountain, so call that x. So with these angles, and then the height of the mountain is h. So with these angles and these right triangles, what sides do we have, this h? What side is that relative to these angles? Opposite. And these side, along the ground here, is adjacent. So we're bringing together opposite, adjacent, and angle. And we have to figure out which one of our relationships does that most directly. Tangent. Tangent of the angle. So we can write two expressions here. Tangent of 1.2637 is, and what is the relationship for tangent? Opposite over adjacent, which would be h over, and what is my adjacent side for this angle? It'd be x plus 25. Okay, and then tangent of 2.0 is our other triangle. Same opposite side, but now the adjacent is just x, right? Just x. Okay, so now we can simplify these and we're home free. So we can write that for this one here, x plus 25, like cross multiply, x plus 25 times tangent of 1.2637 equals h. And then what equals h here? X times tangent of 2.015. Okay, so these are both equal to h. So they're equal to each other because they're both the height of the mountain. So that's, and when you use your tangent on your calculator, make sure you're in degrees. These input values are not radians, but degrees here in the tangent. And so then you'll get those values. And you can simplify to get x equals whatever that is, and that'll be this number of miles here that you are from the center of the mountain when you took that second reading. And then you can get h back from this here. So h is simply tangent at 2.05 times your x. Okay, so I'm not going to work through the algebra. That should be, everyone should be able to do that. Just multiply your, distributing the tangent on the left, gathering your x terms, and solving for x. Questions on B? That's answer B. That's how you find B. Okay, C, how far from you are the top of the mountain at each location? So now we're talking about this. So it's the hypotenuse, called Z1 and Z2, say. You got two hypotenuses to find how the straight line distance. Okay, so once you almost have a triangle solved, then you usually have lots of options of how you can finish it off. So if we have h and we have x after part B, then maybe the easiest way is just Pythagorean theorem. Just you got the two legs, just a squared plus b squared equals c squared. Okay, but if you wanted, say for this smaller triangle here, you've got, say, x, and you want to find, so x is the adjacent side. What is z? Which side is it? Well, it's adjacent, so is it opposite or hypotenuse? That's the hypotenuse, right? So what brings together hypotenuse and adjacent? Which relationship brings together adjacent and hypotenuse? That's cosine. So the cosine of that angle would equal what ratio? Right, adjacent x over z2. And you would know what x is, right? We know what x is from part B, so you could solve for z2. So that's just another way. showing you that once you get close to finishing solving a triangle, meaning finding all its angles and finding all its side lengths, you've got options. You can use, if you've got two sides, you can use Pythagorean theorem to find the third side, or here you could use just cosine to find that hypotenuse given the adjacent side x. Okay? And then you'd find z1 as well. Okay? And then D is a pretty easy problem. It says you're 36 miles away. The height of the mountain's 0.34 miles up. What's the angle? So which relationship are we going to use to find that angle? Sine, cosine, or tangent? So for that angle, 0.34 is which side? Opposite side. 36 is adjacent. So this is tangent. So now when you're doing, just as a warning, when you're solving for an angle using tangent, you're going to use inverse tangent. And you have to know that that answer that you get out from the calculator will be in what range. Right? We got this issue of when we reverse the process, we need to cut the interval of angle down, and then we might have to make an adjustment when we're solving a problem. Okay? So know that that angle, when you use inverse tangent, will be between, remember what we said? It's just like arcsine. Negative pi over 2 to pi over 2, but this time not including straight down and straight up, where the tangent's undefined. In this case, you won't have to make an adjustment because your angle will give you that first quadrant angle between 0 and pi over 2, so no adjustment will be needed. Okay, does that help with this problem? I didn't finish anything, but I got you to the point of just algebra to the answers. Are we good? Okay, so this week you have exam. So we have two things going on. You have the post-test, which is tomorrow or Wednesday. It's the same procedure as all other exams. You got to go to the testing center and take the post-test. You don't have to prepare, but you do want to do as well as you can. So this is scoring. You do want to do as well as you can on the post-test because depending on your improvement from the pre-test, I will give you a bonus on exam 3. At the same time, it's required. It's not just an extra credit exercise. It's required. If you don't take the post-test, you won't get a score at all for exam 3. Okay? So you have to take it. It's a required element. But I'll give you some, if you do well, compared to the pre-test, I'll give you some bonus on exam 3. Okay? So do that. And then exam 3 is Thursday. So that's tomorrow or Wednesday. And then exam 3 is Thursday, and I put up the review outline. Now notice here in the review outline, it doesn't include arc sine and arc cosine, which we finished up when did we do that? Last Monday? Anyway, that's the last material on the exam is arc sine and arc cosine. Tangent and the trig triangles are not on exam 3, but they're on the final. Okay, so tangent and the trig triangles on the final, but the last thing that we covered that will be on exam 3 is arc cosine, arc sine, and applications, but just notice that that's not on the review outline. Okay, so that's important. Weber review problems are up. I put those up last night. Same procedure as exam 2. You can work, again, more bonus on exam 3. I'll give, depending on how many you do correctly, I'll give you a proportional amount of bonus on exam 3. But you have to get credit for that, for bonus, that has to be done by 11 p.m. Wednesday night. Okay? Then after 11 p.m., you still have access to it, but all the answers are there to help you study, okay, and to check for those ones that you need help with, okay? So 11 p.m. Wednesday is the deadline for bonus on the web work. I've also included an archive of quizzes from a prior semester if you're interested. Okay, is there any questions on exam 3? So don't wait till Wednesday night to study. You got to start studying if you haven't already. Especially, it starts in module 6, which is rational functions. So exam 3 covers modules 6 and 7. And module 6 we did over a month ago. So you're going to have to review or relearn that. And then all of module 7 is the bulk of the exam. But there are questions for module 6 on the exam. Okay, questions?
So exam 3 covers up to arc sine.
Right.
And then on the final exam it's triangles and tangents.
Everything on the final. So what we've done since then will definitely be on there. You can guarantee it. Okay? Other questions? Yes, sir?
The post test, from what time to what time?
So same procedure. You just got to be in the door by 10:30, and you can in between 10:30 and 6:30, either Tuesday or Wednesday. Yep. So that's the same. The test, the hours of the testing center are the same every day. So Tuesday, Wednesday post test, Thursday exam 3. And so, of course, of all that stuff that we've talked about, what you actually get on exam 3 is has the most weight for your grade in the class. So prepare for exam 3 and do your best on the post test. Other questions on this stuff? Okay, so that's all available in the exam prep. That outline is available in exam prep, and then web work, same place as always. And you should see that that's up. Oh, and watch out on the web work. Many of the questions you only get 3 attempts, and then the ones with more entry boxes, you get 5 attempts. So just keep track of your attempts. So often students will ask me the question after you've wasted all the attempts. So do it before, right? Do it before. I want to help you to get it correct, get your credit. So ask me the question, email me the question before it's too late to get the credit. Yes?
Is there going to be a recitation on Friday?
Yes, recitation Friday. Yep.
Is it going to be a last one?
Yeah, Friday's the last day of all campus classes. So no more classes after Friday. Monday starts finals. And then don't forget, when is the final exam? Tuesday night. It's Tuesday night, not whatever it says on the university schedule for final exams. Ignore that. Our exam is Tuesday night at 7 p.m. Okay, last chance. Any more questions? Okay. So where am I? Here we go. The 10th, a week from tomorrow night, at 7 o'clock in BAC 316. Okay, we want to talk about something called identities, which become a big part of Trig. So identities, they look like normal equations, but we want to distinguish between something like this and an identity. So this right here should look familiar from your algebra past. Okay, so x can take on many values. So suppose x takes on x equals 1. Then what will the left side equals when x is 1? Negative 1, right? So, and then does negative 1 equal 5? No. Okay, so x can be 1, it just, when it's 1, it doesn't make that true. The statement is false when it's 1. Similarly, when x is 0, it's trying to say that 0 is 5. Well, that's not true. Okay, so x can take on many values, but not all values of x make the equation true. So if we use the quadratic formula or some other way to solve this, we would find that there would be 2 values of x that would satisfy this equation. Okay? There's 2 values of x that make that thing true. Other values of x are valid, but they just make the statement false. Okay? Now what about this? If you put 1 into this, you get negative 1 on the left, and you get negative 1 on the right, if you worked it out. Because if you were to simplify this over here, 1/2 x times 6x is 3x squared, and 1/2 x times negative 8 is negative 4x. And what do we see? So what values of x are going to make this true? You said any value. Agree with that? Yeah, it doesn't matter what value of x you put into this. It's always going to be a true statement. Okay? So x can take on any values, but here every value of x will make the equation true. It'll give you whatever x you put in, you get the same value for the left as the right. Okay, and that's the idea of an identity. That's what an identity is. Okay. So this is not an identity over here, because only certain values of x, maybe 1 or 2, make it true. But an equation such that any value that you can substitute for your variable, if it makes that true, then you have what's called an identity. Okay, and so these become important for trig because with these different trig functions, sine, cosine, and tangent, we see these relationships that are identity-type relationships that are helpful in solving problems. They're helpful in, we've written it in terms of one expression of functions, and we want to write it in terms of a different set of functions, maintaining the value of the expression no matter what we put in for theta. Okay, so this comes into play. So let's start. We're going to build a toolbox of identities here. Okay, so here we've got the unit circle. So this is radius 1, and I've swept some angle counterclockwise from the 3 o'clock position. Is it a circle? Does it look like a circle? Yeah. From here it doesn't. Okay. All right. So can you imagine if I were to represent the sine and the cosine of theta in a right triangle? Can you imagine what that would look like in this picture? Everyone should have an image of what representing sine theta and cosine theta to form a right triangle would look like. So this is, if you're thinking correctly, this is what you should have imagined. Okay, what is sine theta? It's the vertical distance and radius lengths above the horizontal diameter to the circle. And cosine theta, number of radius lengths to the right of the vertical diameter. What's the length of this hypotenuse right here? How long is that? What is the radius of our circle? It's the radius, right? What's the radius of our circle? 1. Where was I? Here it was. One more try. There we go. Okay, so we should be able to easily write an equation that brings together 1 cosine theta and sine theta. What would that be? What would bring together 1 cosine theta and sine theta? And where would that come from? Yeah, we have a right triangle, and so our two legs form the right angle, and our opposite to the hypotenuse is 1. So the Pythagorean theorem says a squared plus b squared equals c squared. So applying that here would be cosine theta, and this means square the result after you take the cosine of theta. Square the result after you take the cosine equals what squared? Tangent theta. Tangent theta squared. Is that right? So in the right triangle, that hypotenuse is just side length of 1. Okay, so we've got our first identity. Cosine squared theta plus sine squared theta equals 1. So you're going to keep your list throughout, start building your toolbox throughout class. There's the first one. It's called the Pythagorean identity because it's based on the Pythagorean theorem. So, question. Is it an identity or is it just an equation that's true for some values of theta? Isn't it true? Is it a true identity? What's that? Is it only true for some values of theta or for all values of theta? Or let me change it here. How about now? Is it true now? And what about now? Yeah, so no matter how you choose theta, the resulting sine and cosine will maintain this relationship because that right triangle is maintained for any theta that you sweep out from counterclockwise from 3 o'clock. You'll always have 1 as your hypotenuse, and then your 2 legs will always be cosine and sine. It'll always form a right angle, so you'll have, that's always true. Now, one common use of this is rewriting either cosine squared or sine squared. According to the Pythagorean identity, what does cosine squared theta equal? 1 minus sine squared. And sine squared equals? So this is a common use of the Pythagorean identity. You'll have, say, cosine squared in some expression that you're using, and it'll help to change it to 1 minus sine squared because they're equal by the Pythagorean identity. Similarly, sine squared is 1 minus cosine squared. Okay. And that's one of the most common ones, and we can see it that it's true for every theta because every theta still maintains that right triangle with cosine and sine. So therefore it's an identity because it's true for every angle measure theta. Okay. What about what's the tangent of theta? So we said this length right here is tangent of theta. It's the number of radius lengths above the horizontal diameter along the 3 o'clock tangent. That's what tangent theta is. But now looking at this triangle, how else could we write what tangent theta is? So just now looking at our triangle with cosine and sine, how could you write what tangent theta is? Yeah. Why? Yeah. Yeah, opposite over adjacent would be sine over cosine. Is it an identity? Meaning, is it true no matter what theta is? We can change theta. Is the tangent still sine over cosine? Yeah. So again, that triangle maintains that right triangle. Sine will always be the opposite side of the angle. Cosine always the adjacent side. And so your tangent will always be sine over cosine. That's identity number 2. It's always true for all measures, angle measures theta. So you're making your list. Okay, here's cosine and another graph. And is that graph, do you see that graph as coming before or coming after the graph of cosine? So is this a variation of cosine that comes before or after? After, right? So if we're increasing x, here cosine starts, and now here this version of this graph starts its cosine cycle. So how far behind is it? What do you suppose that value is if this is 1.5? Yeah, so it's pi over 2. We know pi over 2 is 1.57 radians. So this gray graph is pi over 2 behind Cosine. So how can I write the equation of the gray graph in terms of cosine? Cosine of x plus pi over 2. It's behind, right? It's coming behind, so the angle is lagging behind. So it should be x minus pi over 2. So now when I graph it, it should land right on top. Okay? But look at that graph. Should be familiar as something else. It's sine, right? It's sine. So if you took cosine and had it lag behind by pi over 2, an angle of pi over 2, you get the same thing as sine. And that's what I showed you to start with, the gray one. So there's another identity. Cosine of. So now for angle, I'm generically using x. You can use x, you can use theta. It's just whatever symbol. If you take cosine and make it lag or come behind by pi over 2, then it's equivalent to sine. And so then what would be equivalent to cosine? If sine did what? Yeah, so just pretty easy reasoning here. If you make cosine lag behind and you get sine, then if you make sine come ahead of time or come before by the same amount, you're going to get cosine. Two more identities. True for all angles. Is this making sense? So based on all these things we've built up over the last month, there's been identities here. We've already kind of seen them. We just haven't explicitly brought them out talked about them explicitly. Okay, so here's another one. No, that's not what I want. Yeah, that's what I want. Can you see oh, good. Purple and green. Okay, so look. Start from the beginning. So what I'm representing is our standard angle measure, theta, swept counterclockwise from 3 o'clock. And then the green angle then shows what angle relative to theta. What is the green angle showing? How does the green angle relate to our standard angle? It's not the inverse. Yeah, mathematically though, what is that? The green angle is what angle relative to the purple angle? The same but opposite, right? So we can ask the question, what happens when you put the opposite of theta into cosine and the opposite of theta into sine? And so you can observe here from the animation and figure this out. What if you take the opposite of theta, or the green angle, and put it into cosine? Is there another simpler way to write your result? And same with sine, if you put the opposite of theta into sine. So have a conversation, see if you can figure this out with the person next to you. So basically what we're saying is, what happens when you put the measure of the green angle into sine or cosine? What do you get relative to the purple angle? What do you get relative to the purple angle? Let's see here. Karen, what do you think? So let's start with cosine. So the cosine of the opposite of theta, or the cosine of the measure of the green angle. What is that equal to? Not sure. Michelle? The cosine of the measure of the green angle, what is that equal to in terms of the purple angle? What's that? Negative what? What is the cosine of the green angle? What does it mean? We've been working on this for a month. What does it mean, the cosine of the green angle? What does that give you? Tanner? No, the meaning of the cosine. When we put this green angle measure into cosine, we get something. What do we get? Frank? All right, we get the distance to the right of the vertical diameter. So let's stop this here. So we get the distance to the right of the vertical diameter. Can we write that a different way? What's that? He thinks it's equal to cosine theta. Leah, you agree? It's not because it's the same angle. I mean, kind of. So why is it the same as cosine theta? We get this, but the result is the distance to the right. Doesn't matter if it's swept clockwise or counterclockwise. The result of cosine is distance to the right of the vertical diameter. So what do you notice about cosine of the opposite of theta and cosine of theta in terms of where you are to the right? They're the same. You see that they're the same? You end up at the same x coordinate whether you sweep clockwise or counterclockwise. And so this statement right here is true. See that? Okay, what about sine of the opposite of theta? What's that? Equals sine of theta. You get the same thing, right? Because if cosine opposite of theta equals cosine of theta, then sine of opposite of theta must equal sine of theta, right? What about sine? What does sine mean? Vertical distance above the horizontal diameter in radius lengths. So what about the sine of the opposite of theta? Does it equal sine of theta? But what does it equal? The opposite of sine, right? Because sine, for this first, you see that all those sine values are positive. We get the same distance, but now it's below. So we got to take the opposite of sine to get the sine value of the measure of the green angle. Okay, 2 more identities. So cosine of the opposite of an angle is the same as cosine of the angle because you get the same horizontal distance to the right. Sine of the opposite of an angle is the opposite of sine because the opposite of the angle goes down when the regular sine goes up. So they're equal and opposite. They're equal and opposite for vertical distance. Okay, now I have another kind of what I want you to do is, this is something new now. There's a triangle. It's made up of between these 3 vertices. Using sine and cosine, I want you to write an expression for the area of that triangle. Using sine and cosine, write an expression for the area of that triangle. Okay? Go. See if you can do it. I'm going to draw some more in blue. Anything I draw in blue, you just ignore. Ignore the blue and find the area of this triangle that I've just made. Okay, area of the black triangle. Michael, did you get the area of the black triangle? Any work on that? No, didn't get it. Leah, did you get it? Okay, and so what are you saying? So you're saying the base is cosine? So the base. So you're saying this is the base right here? So really, is this the base? So, I'm sorry, I don't want to put words in your mouth. What did you think the base was? This? Okay, so what's the length of that? That's the base of our triangle. What's the length of that? Is that sine? The sine is from here above the vertical, the horizontal diameter. So then what would 2 sine? And then what's the height of this triangle? If that's the base from there to there. Cosine. Okay, we're just going to leave it like that. Did you get that? You should have gotten 1/2. 2 sine theta, the base is vertical here, and cosine is the height horizontally. All right, what about the blue triangle? What about the blue triangle? Any progress? Angelica? Well, it's still a triangle, so you still have to use 1/2 base times height. So what base and what height are we going to use now? Is the question. Nas.
Base here is going to be cosine.
So the base is cosine. You're saying this right here? You sure that's cosine? From there to there? Well, it's a horizontal distance, but is it the horizontal distance to our point? No, we're talking about horizontal distances. See, cosine is a horizontal distance to the point on the circle. So what's this horizontal distance? No, it's easier than that. It's the radius, it's 1. The base of that triangle is 1. It's just the radius out to the 3 o'clock position. What's the height? Sine of theta, right? That's sine of theta. Is it sine of theta? Speak up if you think something different. Frank. Yeah, the angle here for this terminal side, right? So for this terminal side of this angle is this angle here, right? It's this angle starting at 3 o'clock, swept out to here. Sine of 2 theta. It's not theta, right? The angle swept counterclockwise from 3 o'clock is 2 theta. So now we have that and so these triangles are the same because they both have an angle of 2 theta. So this one's 2 theta here, this one's 2 theta here, and the adjoining sides are all length 1. So these are the same triangle. So if they're the same triangle, they have the same area. And if they have the same area, then we've got an identity here. Sine of 2 theta equals 2 sine theta cosine theta. Did you see what happened? See how I made that conclusion? Those triangles are the same, so their areas are the same. So then base times height is the same as base times height. This is called the double angle identity for sine. Sine of twice the angle is 2 times sine of the original angle times cosine of the original angle. All right, double angle for cosine. We're not going to prove it, not going to show it like we did that one, but it's cosine squared minus sine squared. And then using the Pythagorean identity, cosine squared is equal to, remember what we said? 1 minus sine squared, which when you simplify it makes 1 minus 2 sine squared. And then similarly, sine squared is 1 minus cosine squared. And if you simplify it, you get this. So cosine 2 theta actually has, the double angle for cosine has 3 versions. Cosine squared minus sine squared, 1 minus 2 sine squared, and 2 cosine squared minus 1. I did not show you where those came from. Okay, every other one I've shown you where it comes from, not that one. Okay, I still have one more thing to do. So these are called the double angle identities. What is sine of 2 theta equal to, or what is cosine of 2 theta equal to? Okay, one more thing. So with our standard triangle of adjacent, opposite, and hypotenuse, we had that sine theta was opposite over hypotenuse. Okay, well there's another, and then cosine theta. Okay, please don't pack up. Can you just hold on for 1 second? Thank you. Cosine theta is adjacent over hypotenuse, and tangent theta is opposite over adjacent. There are 3 more, because there's 3 more ratios you can make. Cosecant, secant, and cotangent. Cosecant theta is hypotenuse over opposite. And secant theta is, and because it's the reciprocal, therefore, of sine, we have another identity, that cosecant theta is 1 over sine theta, not to be confused with arc sine or inverse sine. This is different. This is 1 over the sine, because cosecant is hypotenuse over opposite. It's the reciprocal of sine. Secant is hypotenuse over adjacent. So secant theta is 1 over cosine. Again, that's not inverse cosine. It's 1 divided by cosine. And cotangent is adjacent over opposite, so it's 1 over tangent. So there's 3 more identities. And these 6 functions give us every possible ratio in a right triangle. And from those 6 functions, it just opens a can of worms for identities. That's what we'll do on Wednesday. Okay? There's 3 more.
Wherever it leads, I got a board for you without a name on it. It's got a header and everything, just no name. It's 1 page, black thing.
Hey, don't forget, post-test tomorrow and Wednesday, exam 3 Thursday.
It's fun.